Okay, so good morning for pre-calc. We're going to press on for exponential functions here. This is not going to be on your exam, all right? The one that's next week, we are stopping, so we'll just write that first. Exam 1 ends at 3.1, so it's up to and including, see, it's like a bracket, right? Like a closed set, like an interval notation. So exam 1 ends at 3.1. There will be nothing from 3.2 on it, all right? Even though today we'll talk about 3.2, but we will review all of chapter 2 stuff and inverse functions for next week, okay, while you guys are taking that, so that'll be current. We'll be able to do that, but I want to push forward a little bit this week for this because, like I said, logarithms are, you know, if I've taught the college algebra before, and I just have a feeling that nobody really gets logarithms after one semester, and that's normal. Okay, nobody gets logarithms after one semester. Nobody does. So, all right. So here we go. Let's look at exponentials first because that's how you introduce logarithms. All right. And an exponential function looks like b to the x. All right. And we have a little caveat here where we try to say that b is not equal to 1 and b must be a positive number. Okay. So the reason why they do that is because if I gave you an f of x that said -2 raised to the x, right? Well, x can be any number, right? And there's going to be a problem. There will be problems if, say, x was equal to 1/2. Right? You'd have -2 to the 1/2, which is the square root of -2. And again, assuming if you have taken trig, then you're going to get this coordinate system, right? Complex plane. We might be able to graph some of this on the complex plane. It's a whole other class called complex analysis. Okay. But mostly we want to, we want to constrain ourselves to the real plane. It's R2 is what this is called in more advanced classes. But the Cartesian plane, the XY plane, we can't graph this because there's no imaginary numbers on this graph, on this coordinate system. So maybe, but not this class. Okay. So here, no, it's not happening. Okay. And that's not the only problem that we're going to have, right? If I do -2 to the 1/4, this is also a problem, or -2 to the 1/6, etc. Okay, so that's why we say, well, b has to be greater than 0 because we're going to have this. Okay, the reason why we don't want b to be 1 is because, first off, 1 to anything, right? 1 to anything up here is always 1. So we can do silly things like this, where we could have 1 being 1 to the 2, right, is equal to 1 to the 3. And what we're going to do here, the first thing you're going to learn is to equate the exponents, right? If the bases are the same, we're going to equate the exponents, and then you're going to be left with that. And unless you work at Bank of America, this is not a good system. It's not a good solution. By the way, I rip on Bank of America a lot. If you work at Bank of America and you're a teller, you're not the problem. If you're a local manager, you're not the problem. I'm not talking at you. I'm talking about the people who work in San Francisco that run stuff. All right. So that's why we don't want b to be 1, is because, one of the techniques we use is equate the exponents, and if b is 1, then we get this. So we don't want that. Okay. So that's why we're back to f of x equals b to the x. B is any number except for b is not 0, or b is greater than 0 rather, not just not that. B is greater than 0, strictly, and it's not 1. Okay, so that's what we're working with. Okay. Notice the x is in the exponent variable. The x is anything. The b is going to be fixed. Okay, so we're looking at stuff like, 2 to the x, 3 to the x, 1/2, because b, as long as it's bigger than 0, it's fine. 1/2 to the x. Okay, normally we try to keep these numbers pretty small because this graph tends to get really big really fast, and if we have a larger b, it's just going to get worse. Okay, so we have a couple of different things, like our first problem, okay, excuse me, is f of x is equal to 4/3 raised to the x. Okay, the closer this b is to 1, the flatter the line. Okay, so if you have a 10, it's not going to be very flat. It's going to go up pretty fast. But this one is there. So the first thing we do is, okay, let's just plot some points. Okay, so if we say x is 1, so let's do a couple things. Let's put it here. Okay, and we'll do 1 and -1 and 2 and -2. Okay, if we need some more, we can put them in, but we'll just start with this little bit. So all I did was put our basic numbers in here first. Okay, so what's 4/3 to the 0? Right, well, we got a number raised to the 0, this one. All right, 4/3 raised to the 1. Right, if all the problems could be this easy, right? If we do 4/3 to the -1, right, that just flips it, right? This just says take reciprocal. All right, now we'll get a little bit more difficult, and we'll say, okay, what about 4/3 squared? Okay, so we're going to have 16/9. It's not quite 2, right? 18/9 would be 2. This is 16/9. So a little under 2. Okay, and if I do 4/3 raised to the -2, well, first thing is for, right, we have first things first is to take the reciprocal, so it's 3/4 squared, and that's going to be 9/16. So again, 8/16 would be half, so 9/16. It's a little bit bigger than a half. Okay, and then we go to graph this. So first thing I want to ask you is, do you notice that nothing over here is negative? Right, these are all positive numbers. So when I go to graph this thing, I don't really need to write down quadrant 3 or quadrant 4 because we're never going to have anything under there. So here's 1 and 2, 1, 2, -1, -2, and then we'll do 1. I should separate this out a little bit more. Oops, there we go. Come on, that's the one I wanted to get rid of. Okay. So let's not call that 1 here. We'll call this one. We'll say this is 1, and then we'll say this is 2. Okay, this will be a half. So when x is 0, my y value was 1. When x was 1, then we were up here at 4/3. When x was 2, we were at 16/9. Okay, -1, we're at 3/4. Right? And -2, we're at a half. So we're going to get this graph looking like this here. Okay. So I'm going to say pretend that this line is going to go through all these dots. All right. So there's a couple of features that we're going to have here. Okay. If I put in a really big negative number, right? What if I put in -10? Okay. Are we going to get 0 yet? Is it going to be negative? Like, no, we're just going to have 4/3, right, to the -10. That's 3/4 raised to the 10th power. I have no idea what that is, right? It's 0.75 raised to 10th power. Kind of small, 0.05, about a 20th. Okay. But it didn't get, it wasn't negative. How about if we do 0.75 raised to the 100th? I put a negative 100. What do we end up with? Oh, that's pretty small. A lot of zeros there. So what's going to happen is this is just going to get smaller and smaller and smaller and smaller, and it's never going to quite hit 0. So we have a horizontal asymptote at y equals 0 with this function. Okay, horizontal asymptote at y equals 0. Now the other end, this gets bigger and bigger and bigger, but does not give you a horizontal asymptote or a vertical asymptote. It just gets, it goes without bound. Okay, that's what they say. And all of your exponential functions look like this. Okay, they all have the same shape or something like that. Okay, that's always 0, 1. Okay, so you have another function to add to, all of the functions that you knew from before. So if you didn't remember this from college algebra, that's okay. But remember, you had to learn like linear and x squared and x cubed and square root and 1 over x, right? You had to learn all of these, absolute value, right? You had to learn all of these. Well, you have one more to add to your little bunch of things to add here, to know here, is that's exponential. Okay. There we go. So there's just, you're going to get to learn, when you take trig, you get the new 6 more. So we have 1 more for this class, which is logarithms. And then you take trig, and there's 6 more you get to learn. Okay, and there's your basic shapes that you just get to carry around with you for the rest of your life, because you're going to need them when we do modeling. Actually, give me a moment. Why do you need to know these things? All right, so I'm going to guess that a lot of you guys are going to be engineers, maybe scientists, and you're going to see data, right? You're going to do an experiment, and you're going to plot data, and your data, whatever it looks like, you're going to run your little experiments, and you're going to get a shape, and they're going to say, what model fits this shape? And you're going to say, oh, that kind of looks like a square root function to me. Great, why don't we try that? There are other functions that could also fit this. So maybe the square root doesn't work out so well. And you think, oh, again, we'll get to this with logarithms. Maybe you decide, oh, logarithmic model might be a bit better. Okay, so let's go with logarithm versus square root. Okay, so the more shapes that you happen to know, right, when you have this data, you say, well, what kind of relationship can I make? You're going to use these shapes to kind of say, well, this is a generalized relationship for this data. Okay. Sometimes you're out of luck and you got nothing. Okay. There's other methods for that. I tell people a lot of times that being a math major, like one aspect of being a math major is you get to play connect the dots. And I'm not kidding. That's really a big field in math, is how to connect all the dots. In statistics, we got a lot of dots, and we just say, here, they're connected. We drew a line, okay, through a cloud. But there's more sophisticated ways to do all of that, okay? This is the easy way. So that's why we make you learn the shapes. Is later on, you're going to have to say, what shape is this? Okay, so let's go ahead and take a look at your homework here, okay? And we have to graph a couple of different points, okay? Does it say how many we need? No, it doesn't. Now, we could use the pencil, but you just saw, like, none of those, only 0, 1 was a nice number, right? Everything else was a disaster. So we're going to plot anywhere. We're just going to use this. We're going to say, okay, well, 1 and then 4/3, okay, and have it plot that way. And then maybe 2. I don't want to try to estimate that with a pencil. Are you kidding me? With the way I draw? No way. Let's go with -1, and then 3/4, right? And -2. It tells me I don't have enough dots. I'll tell you, I'm going to be a little upset. Okay. plot point. All right, so there we go. So we'll go ahead and we'll place our asymptote. We're placing our first point and place any other point. And notice that I only needed 2. Technically, you do only need 2 points. It's kind of like a line. You only need 2 points for exponential function. Okay. But, you know, if you had to do this with paper, pencil, and you didn't have this tool, then this is how you would do it, right? You would plot these points and then you draw a line through them. But since you know what the shape is, you know how you're going to guess. Okay. So that's, and all the usual graph transformations. Okay, I know you all loved graph transformations and can remember all of those things. So that's what we have for that. I wonder, what's part 2 for them? First point's always 0, 1, right? And then, oh, they are really, let's not do that. 0, 1. Plot point, and it's 4/5 to the first power, right? So that if I put in x equals 1, we get 1 and then 4/5. We can plot that point, okay? So if we go through and say that, and now we're going to have our point, our second point, okay? So notice it let me do it immediately when I plotted it. I didn't have to mess with it. But if I didn't plot it, it's going to force me to be on on the grid. You don't want that. Okay. Oh, okay. They just went to domain and the range. I thought they were going to ask for something interesting. Okay. So x equals 4/5. Okay. And the domain, well, we showed up here, right? There's no x's I couldn't choose that wouldn't give me a value. Any x I pick, that'll work. Okay, so the domain is all real numbers. Okay, you used to write it like that. I think some people have a fancier R. In interval notation, we get to be boring. Okay, that's how we write it. All right, the range, any numbers that are smaller than 0? No. So the range is just going to be y is greater than 0. The way we have to write that in interval notation is we never quite get to 0, and then we go up to positive infinity. Okay, so that's our domain and range here. All right. Oh, C of x, sorry. So let's see, for domain is going to be negative infinity, positive infinity. C is going to be, again, right, we never get to 0, but it goes up, up, and away. So wait, it's getting smaller. Like, yeah, not in this direction. Over here, it's getting bigger and bigger and bigger. So we don't care about which direction things went into. Let's see what do they want us to do here. All right. Like I said, graph transformations. Okay, let's talk about graph transformations a little bit. So this is not quite as intense as it was in college algebra. All right, you already learned that, so we're just going to kind of assume that you're good at it. I don't know what your college algebra teacher did to you for graph transformations. Whatever they did, I hope it wasn't too insane. But there's a lot of different graph transformations, right? We can have y is equal to. I'm just going to write them out. Okay, we have a f of bx minus c, okay, plus d. Let me rewrite this a little bit. So we have a f b x minus c over b, right? Because if I factor that out, right, plus d. And do you remember what these did? Okay, so this was a stretch or compression, right, in the vertical direction. Okay, this one was a vertical shift, See, you know what I really should have done was be clever and did something like this, right? So D, that's a vertical shift. It was in the direction of the sign, right? Plus meant up, minus meant down. Okay. If A was bigger than 0, right, we got a stretch. If A was smaller or A was less than 1, then we got a compression. And the negative, right, the negative would flip it. Okay. So we'll put in a possible negative here. And this would a vertical flip. Okay. Now you remember what goes on in here. So let's go ahead and I guess we can just pick for that. We'll say B. And this was a horizontal. Right? And the stuff, the horizontal always works like the opposite you think it ought to. So if, right, if B is a big number, B is bigger than 1, then it was a horizontal compression. And if B was smaller than 1, then it was a stretch, a horizontal stretch. Okay, and the idea is that each and every one of these can be something, but it's the height of cruelty to put them all in, because after a while, it's like, these are supposed to make your life easier. I swear to you, that really is the case. They're supposed to make your life easier. But if they start to get like too difficult, then at a certain point, it's like, I'm not going to use my transformation knowledge. I'm just going to start plotting points and figure out what's going to happen, because it isn't easy anymore. Okay, this was a horizontal shift. So if there's 1 or 2, yeah, I'm going to use the transformations because it's easier to do that than it is to plot the points. But if you throw all of these things in here, it's like, no, I'm done. I'm just going to plot points. The hell with it. Okay. And again, if it was positive, right, it went to the left. It was negative, it went to the right. So it's not to the point where you're going to throw all of these different elements into you at one time. You're throwing 1 or 2, and usually one of those 2s are going to be a vertical shift here. Okay, you don't want to do too much of making everything kind of crazy. Okay, but just to remember kind of, you know, what they were, right? If there was a negative on the inside, that was a flip. It was a horizontal flip. Okay, so let's see here. They are going to ask us to do 4 to the 4x. We're going to do 4. We're going to q of x is equal to 4 to the x plus 4, right? Plus 2. So without doing very much of anything, can we just diagnose and see what they're asking us to do here? Right? We're just going to remember that that's going to be some kind of a vertical shift up. And then this is going to be a horizontal shift. The way it's written, this is a horizontal shift. And since it's plus, we're going to the left. Okay. So when I'm graphing my function, right, just to sketch it in, 4 to the x. And then what we're going to do is, what did I use for vertical? I used red. So with this plus 2, instead of going through 0, 1 here, we're going to go through 0, 3. We're just going to add 2 to that. And we're going to have a function that looks something like that, right? It's still going to be very steep because 4 is a big number, relatively speaking. And instead of having our horizontal asymptote at 0, we have y equals 2 is now our horizontal asymptote. Okay. And then we have this business, right? We actually have to shift it off to the left. What did I use for a shift here? Was that brownish color? Okay, I think it was this one, wasn't it? Does that match? Sort of, yeah. Okay, so then we're going to shift this thing, right? Because this thing is a horizontal shift off to the left. So instead of going through this point here, right? Instead of going through 0, 3, it's going to go through 2, 3, 4. It's going to go through negative 4, 3 here. And then we're going to have a shift that looks something like that. All right. Now, this is the maybe not the crummiest drawing in the world, but it's pretty close. All right, to the worst drawing you could ever make of this thing. But it does give me an idea. Like when I'm going to go ahead and draw, if I wanted to do this a little bit better, I'm going to draw my coordinate axis like this because all the interesting stuff happens over here, right? And it's pretty far up. So I want to center up where the interesting thing is happening. And it just gives me an idea, like, okay, well, what am I expecting to happen? Okay, and this isn't too bad, right? This function isn't too bad of tracking what's going on. That I'm going to plot some points, but I'm going to have a general idea of what's happening with this shift anyway. Okay, the only reason I might plot some points is because maybe I'm not quite sure about what's going on here. Okay, so, okay, use the, oh great, look at that. They give us a, oh, wow, what a cool tool this is. So use transformations to graph the given function. Well, we're going to go up 2. All right, we went up 2. And then what we're going to do is we're going to move this thing 4 to the left, right? So 1, 2, 3, 4. Oh, that is a nice tool. Wow. But they did a good job. Okay. I just really think it's cool that they make you pick it up and move it, because that's exactly the metaphor you should be thinking in your head, is like, I'm just picking this up and moving it. Okay. Domain. Okay. Domain is fine. It's still everything. Okay. Still all the real numbers. However, the range, right? What's the smallest number we get to? Well, we kind of get to 2, but not quite, right? Because it moved it up. So we're still here. Now we're at 2, and it still goes pretty far up. All right, equation of the asymptote, y equals 2. All right, so just going back and remembering that, okay, all of the things. The one I want you to remember more than anything else, really, is what about how are b to the x and b to the negative x related, right? Let's do it this way. And b to the negative x. All right. Well, b to the x, right? Assuming that, assuming your b is well, assuming x is a positive thing here. Actually, it doesn't have to be. Okay. B to the x looks something like this, right? And the negative one is just a reflection, right? It's a reflection about the y-axis. So we're going to be getting something like this, right? I'm trying to reflect it. So it looks like a mirror image. So hopefully it does, at least a little bit. What does it look like with numbers? Right? It looks like maybe we have 2 to the x or 2 to the negative x. Well, 2 to the x is just that, it's 2 to the x. But 2 to the negative x, this is really 2 to the x, or 2 to the minus 1 to the x. All right? This is 2 to the minus 1 to the x. Because remember, right, in order to simplify a power to a power, we just multiply them. But we can do them opposite, right? We could take a part of multiplication and make it a power to a power. And 2 to the negative 1, that's 1/2 to the x. Okay, so 2 to the negative x is 1/2 to the x, and that's what the negative sign is doing, but it's also doing this. It's making reciprocal. Okay, so that, I want you to just be aware of that one, because that one happens pretty often. We're going to see, e to the x or 2 to the x a lot, but it's also very common that we're going to get some kind of a decay function. And you're going to have a negative up here. So don't be, looking at this like, I've never seen this before. Like, now you have. It just means it gets smaller and smaller. That's all it means. Things are dying. Okay. All right. Speak of the devil. Okay, speak of the devil. We have use transformations on the graph of 2 to the x to do this one. Okay. And since we're reflecting, there, it's just going to go the other way. All right. We don't have to move it up or down. It's just going to go across this way. All right. So that's, yeah, we're just doing a lot of graph transformations here. Okay. And again, the way you're supposed to, the way they lead you to do this is exactly the way that you really should be thinking about it. The reflections and the picking things up, that's exactly what you should be doing. So 1/3 to the x, well, the first thing we could do is we could flip it, right? Because that's what this negative here is doing, it's flipping it. And then we're going to pick it up and we're going to move it down 1. All right, and that's what this should be looking like. Okay. And in domain and range, again, you pull that off of the graph, right? You could do that. Okay. Okay, let's go talk about E for just a moment. All right. Okay, E is a very important number for calculus. It's a very important number for physics. Mostly because when you want to do calculus on e to the x, you don't have a scaling factor that comes along for the ride. If you have a 2 to the x or a 10 to the x, like regular stuff, when you do calculus on this, you have scaling factors that you have to remember where they go. So if you're working in a science that cares about how things are changing, like that's the most important thing is how things are changing, they want to use e to the x or eventually a natural logarithm, because in that change, because calculus is doing change, we don't have scaling factors that you have to keep track of. Okay, if you're working in a science that doesn't really care about how things are changing, you just want to measure like how big things are, then usually we use 10 to the x or base 10 logarithms. Okay, which we'll get to. So for the things that are changing, we care about, we're going to use E instead. Okay, and I don't know exactly how your instructor maybe have introduced this to you, but here's what the little game that I like to play with you. Okay, we're going to borrow $1 at 100% interest. What we're going to do here is we're going to change the compounding so it gets smaller and smaller and smaller. So we're going to do it compounded once per year, compounded 4 times a year, compounded 52 times a year, etc. And if you remember your compound interest formula, and I'm sure you do, okay, that's this was equal to P1 plus, right, R over N raised to the NT. Number of compounding periods. R was interest, APR, as a decimal. Okay, this is the actual formula that banks use. I don't know if you have a savings account, but if you do and you have money in it, even in the 70s, okay, even when I had a savings account, I still have one, but the interest was small. It was like 3%. It's like, ooh, after a whole year, you get 3 pennies on your dollar. Now it's insultingly small. Okay, so if you get really, really, really big numbers and like T isn't huge, then you should question that you made a mistake. And that mistake is going to be right there. You forgot to change this to a decimal. Okay, so unless you actually are working at a title loan company, your interest, your your values here should be, you should not see excessive numbers, okay? Again, assuming interest is real. As soon as you start doing loan sharking and you get like, you know, that, then you're going to get weird and numbers that blow up, okay? But that's something to worry about. If you're seeing weird numbers and it looks like a completely reasonable problem, and you're like, wow, if I invest like $100 for 3 months, I'm going to have 3,000. Like, no, you're not. No, stop right there. You screwed this up. Okay, at least. T is in years. Okay, there it is. That's the biggest mistake I see from students is they'll say 3% interest, and instead of saying R equals 0.03 for 3%, they'll put in 3, which is 300%. So, you know, again, you're either a very good candidate to be working at a title loan company, or you've made a mistake, and you probably want to check that mistake first. Okay, because your word for the day is usury. Okay, that means charging, that's what loan sharking is. You're charging excessive interest. Okay. All right, so we have a pared down problem here. Okay, so we have the amount is equal to principal, right? And then we have 1 plus, and then 100% interest is 1, and then n, right? And then we're only going to borrow this money for 1 year. Okay, so we're just going to have to the n here. So very simplified problem of what's going on here. Okay, so what happens if we compound once per year? Right? We have 1 plus 1 over 1 raised to the 1 power. Well, we could do this on this one. I could even do in my head, right? 1 plus 1 is going to be 2. 2 raised to the 1 times 1. Okay, so we borrow that $1, right? At the end of the year, you got to pay back $2. Okay, which is obscene. Okay, this really is. What if we do it compounding quarterly? N equals 4. Okay, so we have 1 plus 1 over 4 raised to the 4th power. Okay, let's see what happens. Okay, so we get 1.25, right? That's what 1 1/4 would be, 1.25, right? $1.25 raised to the 4th power. Right? So if I compound 4 times a year, right, we got to pay back $2.44. Right? We're going to keep a whole bunch of decimals here. Rather than put the decimals here, we're just going to keep track of them over here, because normally in class at this point I remember I'm like, oh shoot, I need to see decimals. So we could loan $1 million a year, or we could keep decimals. How about n equals 50, right? 50 times a year. It's like every week. Okay, so let's do 1 plus 1 over 50 raised to the 50th power, and let's see what happens. 1 plus 1 over 50 raised to the 50th power. It's 2.69. Right? How about we do daily? Okay, the n is equal to 365. 1 plus 1 over 365 raised to the 365. What's that? Okay, and then raised to 365. Okay, so 2.71. We went from doing it every week to every day, and how much more money did we get? We got 2 cents. Okay, for how much increased compounding we did, we grew an order of magnitude in compounding, and we got 2 extra cents. Okay, so it's not going up very fast here. What if we did it every hour? How many hours are there in a year? Right? 365 days to a year times 24 hours. So 8,760. Okay. 1 plus 1 over 8,760 raised to 8,760. Let's see what that is. 1 plus 1 over 8,760 equals, and then raised to 8,760. Okay, here we got 2.718. So 2.72, okay? So again, like, you know, you started doing it every hour and you made 1 extra penny if you rounded, okay? Could we keep going? Like, could we do seconds? Could we do nanoseconds? Okay. What's going to happen is the bigger and bigger this number gets, okay, we say, we'll do it this way. We'll say as n tends toward infinity, or as n grows without bound. That's the poetic way of saying all of this. Okay, we have 1 plus 1 over n raised to the n. This number, bigger and bigger and bigger, doesn't really get much past 2. Doesn't get much past 2.7. This goes to e. Okay, that's how we get e. Okay, and e is approximately 2.71828182885. And then it goes on, kind of like pi. Okay, doesn't repeat. So the reason I know that, so here's your American, see, look at all of this. This is an amazing lesson. You guys got a new word, you got a new number, and now you're going to get a new historical fact. 1828 was when Andrew Jackson was inaugurated. The only reason I know that is because the guy who taught me this stuff when I math for this, he was like a giant Andrew Jackson fan. I'm like, okay, whatever. That was not a good president, but you know, back in the 80s, it didn't have the connotation it does today. He was not a good president. If you ever look up Trail of Tears, Andrew Jackson's name is right next to that. So not a good guy. All right, but that's when he was inaugurated. Okay, so that's you know, there's your American history lesson for the day, as well as your vocabulary and your Sesame Street of a new number. Okay. There's other ways to get e. It shows up a lot. It's 1 plus 1 over 1 with an exclamation point, plus 1 over 2 with an exclamation point, plus 1 over 3 with an exclamation point. Goes on for infinity, which is why we talk about polynomials, we make a big deal about the fact that this does not go on for infinity. Okay, because if it does, it turns into this stuff. And 3 factorial, that's not just a really excited 3, okay? That's 3 times 2 times 1. It's factorial. Okay. I used to know what that was off the top of my head because in statistics and probability, you have to do this one a lot. Okay, but 52 times 51 times 50, all the way down. 0 factorial, that's defined to be 1 for now. Okay. You get to about halfway through Cap 2. We're going to cover that, I think, today or tomorrow in Cap 2. There's another way of doing this. Okay, but for now, for you guys, 0 factorial, that's 1. Okay, so I can make that happen. It's 1. Okay, but that's how you could also get e. This idea made a lot more sense to me than this idea. So whichever one you're more comfortable with, you know, you can think about it. We're going to use this one a lot, especially when you get to Calc 1. You're going to see this a few times, a few times. So this in Calc 1 is more important than this one is. But in Calc 2, we use this one a little bit more, and then we can see what that's going to happen. Let me just show you one thing, and then we'll call it. Okay, got to show you a new number, so I should be very happy, right? So if I go here and I go to Desmos, okay, and I type in y is equal to e to the x. Okay, this is really neat. We can approximate that with a polynomial. Those were two. So the idea is I'm just looking at it for a small value, right? And so, well, e is approximately this polynomial. If I just look at it around 1, then that's not a lie. That's actually true. But then here we do the x to the 3 divided by 3 factorial, right? Plus x to the 4th, x to the 4 over 4 factorial. And if I take this thing out, an infinite value, we are going to, as far as x greater than 0 goes, right, as far as looking at this side of the curve, that's going to get a better and better and better approximation of this thing as we go forward. Okay, so we could string this thing all the way out, and we're going to get really close to what e to the x is. Okay, so that's just kind of a cool thing that you're going to learn how to do more of in Calc 2. But just to kind of draw the connection between e to the 1, and if I replaced all my x's with 1s, right, that's how come it looks almost the same. Okay, so I'll stop us there, okay, and stop talking about e so much. But it's a really cool number, and if you're frightened of it, don't be frightened of it. It's very helpful when you get to calculus. You're going to find working with e to the x easier than working with 2 to the x or 3 to the x. Okay, so I'll let us go there. You guys have a great afternoon. I put the videos from the last couple of days up recently, so you guys can see those if you need to go back. And again, try to get through 3.1. You can probably go forward a little bit to 3.2, but we'll do an intro to logarithms tomorrow on the next day. And next week, I'll review of stuff that we've done up to the test here. Okay? So I'm going to stop us there.